variation. Okay, if we have inverse variation, so inversely proportional, and the example I was trying to use was pressure, and pressure is inversely proportional to volume. And what that means, if I'm drawing a graph, if I draw a graph here, and my vertical is pressure, let's see, if pressure is by itself, it's the dependent variable depending upon volume. So pressure is the vertical, and that'll be measured in pascals. I'm trying to hard. That's supposed to be a lowercase a. That's supposed to be a PA for pascals. And then the horizontal is volume, and that'll be in liters or meters. We should be in meters cubed. Well, for this one, it's probably going to be liters. We're talking about gases and gas laws. Since it's an inverse relationship, what we get is a shape sort of like this. Okay, it flattens out a little more when we get there. Let me undo that part. Okay, so that's an inverse relationship. By the way, a direct relationship would have been just straight out. Now the angle can change for one particular direct relationship, direct proportionality. So sometimes it's going to be very steep, sometimes it'll be very shallow, and sometimes it'll be more out in here in the middle. But every direct relationship is going to be a straight line sticking out of the origin. Inverse, which we're talking about now, is this little curve here. And all that means now is that, again, you'll have to be told in a problem pressure is inversely proportional to volume. For a 1.5, the pressure is at 1.5 atmospheres. Well, I had pascals there. Actually, probably these will probably use, well, probably more likely to use atmospheres. They'll give you a pressure and they'll give you a volume, and you again find the K by the methods we talked about in class, by the methods from algebra. Here we would multiply by the volume on both sides, and that would get the K by itself. Take the pressure you're given, 1.5 atmospheres. And let's say it goes with a volume of, say, 0.75 liters. Well, if we isolate this K, we'd do it by multiplying by volume on both sides, multiplying by V on both sides, and we would wind up with K equals PV. I guess I am going to go ahead and show you the details. I said earlier I wouldn't, but I'm just a sucker. And so we do pressure times volume, so 1.5 atmospheres. It's getting harder to write with the mouse, guys. So I apologize for the messiness. Times, I'm just make an X here. Times 0.75 liters, and I'm not doing that in my head. Let me bring the calculator up on the computer. 1.5 times 0.75 equals 1.125. Okay, we've only got two decimal places here, or two significant figures there, so we're going to do 1.1 is our answer. Okay, so that equals 1.1, and that's atmospheres times liters. The way you do units that are combined and just times each other, we just put a little dot here. That's more of a dash. Sorry, again. I'm not writing on a board the way I normally would. That gives you the K, and then they would come up with the third part of the question where they give you only one thing and you have to find the other thing using the given value and the K that we just found here. They may tell you the pressure to find the volume when the pressure is 3 atmospheres, or find the volume when the pressure is find the pressure when the volume is half a liter. Let's do one where we have the volume. That way it's one of the easier ones. We don't have to move, because sometimes you don't have to move it around. So let's say that we're given that the volume is let's say it's 3 liters. What's the pressure? Well, we just plug in P equals, it's K over V. Well, K we know is 1.1, and that's atmospheres. And yes, you need to write units every single time. That's why I'm still doing it, because I'm supposed to be setting the example, even though this is getting kind of messy. I know, I'm sorry. That should be an A, not an R. 1.1 atmospheres, ATM. And divide that by the volume, which is 3 liters. And so my pressure winds up being, let's bring up the calculator, and we clear that, and we do 1.1 divide by 3, and we get 0.36 repeating, so we only have 0.37 atmospheres. Oh, I'm sorry, the units on top up here should have been atmospheres times liters. Maybe some of y'all caught that and were shouting at the screen. Well, I hope some of y'all caught that. Maybe not the shouting at the screen part, but the K had units of atmospheres times liters, so that part goes there. And so we wind up with 0.37 atmospheres as our answer. That's inverse proportionality. Those are the two you're most likely to get: inversely proportional and directly proportional. In every one of these cases, it'll be set up as, you'll be given pressure is inversely proportional to volume, or pressure is directly proportional to temperature, or it will give you the equation P equals K over V, or P equals KT, or F equals KX, something of that nature. They'll either tell you in words the proportionality relationship, or they'll give you the equation. Then they'll give you a pair of information, like an ordered pair, like X and Y. It's just not X and Y. These are the quantities that have more meaning than the generic graph coordinates. You'll use those two values to find the constant of proportionality, and then it'll say some words to the effect of the situation hasn't changed significantly, but we've changed the two numbers that we've had. Okay, we've changed it enough that these two change, but we haven't changed the system, so the K is the same. With the spring idea, it would be the same spring. With this pressure and volume example, or if it was a pressure and temperature example, it would still be the same gas. So they would be probably isolated in a chamber, and you're moving the plunger. So it's still the same gas sample in the same chamber and whatnot. So there hasn't been any significant change that changes the K. And then what they'll do is they'll give you one of the values, and they'll ask you to find the other one, because now you have the K. All right. Now, there is the possibility